Okay, so this closes out the first week of lecture. Like I said, I'll probably send the link about 5 minutes before class for the rest of the lectures. I usually just like for the first week to give like 8 to 10 minutes just in case, because at the beginning of I think it was last semester, the first couple of days there was internet issues. Well, it wasn't actually internet issues; it was YouTube server issues that caused a lot of confusion because I had to keep stopping and restarting stream. And this semester too, it's likely to happen that sometime I will be lecturing and the stream quality will be terrible, or there will be stuttering, and that will be because of YouTube server, most likely. So in that event, I'll stop and restart the stream. Sometimes I'll have to just upload a stream later. But anyway, so doing it early lets me take care of that without causing too much confusion in like the first week or so. So anyway, not a big deal. If you're watching these later, you can always fast forward, and I'm starting at 11 anyway. So okay. So just to remind you of a couple things, we had defined some algebraic operations on vectors. So for the entire course, when I write a vector, say I write the vector that I'll call A. When I write a vector like this, I'm assuming that I'm writing this vector in the following form. Right, so it has components A1, A2, A3. Same thing if I write B. This is B1, B2, B3. I recall from last time that if I add two vectors, this is just the vector that sums the components. So the corresponding components are summed. So it's the sum of the first two components is its first component. Second component is the sum of the second component, and so on. Right? And of course, this is similar if the vectors in question are vectors in the plane instead. I've written vectors in space, but of course, in the plane I would only have two components here. So then if C is a scalar, actually since I've done A, B, and C, well, I'll still leave this as C. So if C is just some real number that is, so C is a scalar, then of course scalar multiplying a vector is just multiplying by the real number C in each slot. Right, so CA1, CA2, CA3. Okay. As we saw, this actually scales the length of the vector. Since we mentioned length, what is the length of a vector? What is the length of the vector A? This is the square root of A1 squared plus A2 squared plus A3 squared. So it's the square root of the sum of the squares. Okay. This is how I compute the length of a vector. And of course, this is related to the fact that you might notice what's going on here. A vector is a point, right? So we have listed these vectors as ordered triples of real numbers. Okay, but that's a point in space, right? And of course, the way that we're viewing this is that a vector is the point in space that is associated to the vector that has initial point, the origin, and terminal point, whatever that point in space is. Okay. All right. And so last time we saw that scaling this vector scales the length. In fact, we can prove this, right? If I compute the length of C times A, well, what is that? Here's what C times A looks like. So just using the same formula, this is the square root of CA1 squared plus CA2 squared plus CA3 squared. What is that? Well, squaring all these terms and factoring a common factor of C squared out, this is C squared times A1 squared plus A2 squared plus A3 squared. All right? So I have factored out, so if I just squared all these individually, this would be c squared a1 squared plus c squared a2 squared plus c squared a3 squared. Right? So factoring out that common factor of c squared, this is what I get. So now I have the square root of c squared times the square root of a1 squared plus a2 squared plus a3 squared. What's the square root of c squared? Now you might be very tempted here to say, oh, square root of c squared is c. Right? But remember, square root of something squared is just a fancy way of writing the absolute value of that thing. So this is the absolute value of c times square root of a1 squared plus a2 squared plus a3 squared. That's the length of a. Okay. This is the thing that tells you that if you compute the length of scalar multiple of a, it is the absolute value of that scalar times the length of a. So a scalar scales the length of a. Okay. Now, recall the picture that we had last time. I don't have the paper in front of me, but recall the picture we had last time that compared, say, a vector a to like minus 3a. What was minus 3a? Minus 3a was the vector that pointed in the opposite direction of a and was 3 times as long. So it didn't matter that it was a minus 3. It still scaled the length by a factor of 3, right? And that's because of this formula. Okay. All right. So those are some nice things to remember. Now, a couple of things I wanted to note here about terminology. So one, remember that there was a 0 vector for R3. That's what it looks like. The 0 vector for R2, of course, is likewise the point that is associated to the origin in R2. Okay. Now, couple more things that I want to talk about. So let me draw a picture here. So let's draw a few. Oh, I didn't really draw those that well. Okay, we're gonna pretend that that's the same length and they're pointing in the same direction. All right, so here's, oh, I'm off screen a little bit. So here's a list of some, or here's 4 vectors, okay, in R2. Now, the question is, let's do one more. Hold on, let's do one more. Okay. The question geometrically is to ask which of these vectors are parallel to some other vector listed here. Parallel, right? So in the usual sense of what we mean when we say parallel has to do with lines intersecting or not, right? So if 2 lines are parallel, then they don't intersect, right, in the plane. But if I'm looking at these, right, we're thinking of these vectors as being these, here's the entire object there. And of course, all these 5 vectors that I've drawn don't touch one another. So are they all parallel, right? Like in this sense? So the answer is no, they're not. So what we mean when we say parallel is, here's a bunch of vectors. Imagine that we took them and we extended the lines, or we extended these vectors into lines in the plane. Again, I told you that I did a bad job drawing some of these. So here's what I wanted to happen. Okay. Okay. Here's this one extended into a line. And here's this one extended into a line. Now, it's clear once we do this, which of these should be called parallel and which would not be parallel, right? So the main confusion is, so then which of these are parallel, right? So these three that I'm marking with a red check here, these are all parallel lines, whereas these other two lines associated with those other two vectors, they clearly intersect these other lines. And so these three that I marked with the red check are parallel. Now, what I want you to note is that the vectors I started with, right, clearly this vector and this vector are not at the same place here, right? So this vector sits here and this one sits at the origin. Of course, this one, not only is it not at the same place, it's clearly longer than the other two, right? So two vectors being parallel can't have anything to do with length, because this vector extends into this line, this vector extends into this line. These two lines are parallel, and I want to call those parallel. Okay, now you might have one other objection. You might say, well, technically, right, every vector, I just said that a vector, last time I said vector is an arrow, so it's a length and a direction, right? It's a magnitude and a direction. So really we can consider every vector sitting at the origin. So if every vector sits at the origin, then doesn't every vector touch, right? Aren't they all parallel? Or sorry, aren't they all not parallel, because every vector touches every other vector because it sits at the origin? We don't care about the vectors touching. What we care about is that if we took those vectors and moved them apart, that if we drew these lines like this, we would get parallel lines. Okay. Notice that, and you might say, well, that's cheating. If you're taking the vectors and moving them apart, wouldn't any two vectors be parallel? Clearly not, because here's a vector that is apart from these other three vectors, right? This one, maybe I'll circle that in black. So this one and this one, these two vectors have been moved apart. They've been moved away from the origin. But when I extend these lines, I clearly get lines that aren't parallel. Okay, so then what does it mean for two vectors to be parallel? It's a lot easier than having to draw a picture like this. Two vectors are parallel. Of course, I drew this in the plane so that you could see what's going on, but the same picture works in space. It's just trickier to draw. So the definition, two vectors are parallel if, so we say that they're parallel if what? So let's think about this for a second. These two vectors look like they're the same length. So if I were to move this vector here, they would like coincide. But if I took this vector and moved it here, it wouldn't coincide. It would be longer than these other two. Right? Well, what does that mean? It means you can stack them on top of each other. They point in the same direction. So that's what's important here. These two vectors point in the same direction. And someone just asked, what if one of them points in the opposite direction? We will also call those parallel. And that might seem totally ridiculous, but in a sense, pointing in the exact opposite direction is the same as pointing in the right direction. Now you might say, how can that be? When we say direction, when we're caring about being parallel, we mean the line of direction. So remember that picture from last time where I took the entire collection of all scalar multiples of a vector. It formed a line, right? It formed, say, the line going in this direction, the half line, and the half line going in the other direction. That's the opposite direction. So that's a full line, right? There's the one going here and here. So that is this direction and the opposite direction form the line of direction here. Okay, so two vectors are parallel if they are scalar multiples of each other. So example. So let's have vectors u, -1, 3, 7. Let's let v be 1, 1, -2. Let's let w be 3, 3, -6. Actually, let's do -3, -3, 6. There we go. That's even better. Okay. So if here are my three vectors, then v and w are parallel since w is equal to -3 times v, but u is not parallel to v or w. Okay, so v and w are parallel, but u is not parallel to v or w. Okay, and of course this is easy to see if you have two vectors written out. It's really easy to see if one's a linear or if one's a scalar multiple of the other. You can just go component by component, right? Right, exactly. So someone just said you can still determine which ones are parallel without translating them away from the origin because they'll have the same slope and they'll lie on top of each other. That's right. So being parallel really means pointing in the same direction, where same here also includes the exact opposite direction, right? But no other direction. So whatever the direction the vector is pointing, you're allowed to point exactly in the opposite direction, but no other direction. Okay. All right. Okay, so that's the notion of two vectors being parallel. So one more thing I wanted to say before moving on, because this is going to come up a lot, and I think I'll have covered all the basics, is the following. There's one additional way of writing vectors, which you might have already seen in physics. So an additional way of writing vectors. And you might say, like, why is this something that I do instead of just writing it in kind of the more compact and convenient way of using components? This has some niceness to its algebra, and it also meshes well with things that will come later. That we won't necessarily do in this course, but things that will come later after this course. There's a lot of formulations involving these things that if you've seen this, it's not a stretch to add one extra component, add a little bit of rules here. So it is important to see this notation, and in fact, in this course, for the remainder of the course, you will use both of these. Of course, if I don't tell you what to use, you can use whatever you want, but in a problem, I may give you a vector in this notation. So this is called IJK notation. So we can write a vector, let's say a vector A, which is written in this normal way, A1, A2, A3, as A, which is A1 times a vector I plus A2 times a vector J plus A3 times a vector K, where I is the vector 1, 0, 0, J is the vector 0, 1, 0, and K is the vector 0, 0, 1. Okay. Now, if you've had any linear algebra at all, then you immediately see what's going on here. All you've done is you have written a basis for R3. IJK, these vectors form what's called the standard basis of R3. I'm not going to use that terminology in this course, but you're going to see this plenty going forward. Okay, and what that means is that this is basically three vectors that are the most convenient vectors that allow you to express any other vector as what's called a linear combination of those vectors. So this is a linear combination of the vectors I, j, and k. Now, why can I do this? So first of all, there's a couple of properties. Before I go on here, I wanted to mention some quick algebraic properties, right? So quick properties, and I mentioned this at the end last time. So if I am summing two vectors, it doesn't matter in what order I do that. This is commutative, right? So vector sum is commutative. If I scalar multiply a sum of vectors, well, I can actually sum the scalar multiples of the vectors to do this. Similarly, if I say sum in the scalar slot, right, this is exactly what you expect it to be. So you have a distributive property both with your sum occurring in the vector slot and in the scalar slot. Okay, that's a way of thinking about this. Okay. Of course, you know, there's some other obvious properties. I'm not going to list everything just because there's no need, because most of these are obvious. You have an associative property of vector addition, so you can do this in either order, right? And so on. Oh, I put 2 twice here. That's no good. Okay, we'll put that as 4, I guess, right? Of course, the thing, very important thing that I mentioned last time, which is adding the 0 vector to any vector just yields the vector you started with, right? And then scalar multiplying any vector by 0 yields the 0 vector. Okay, so here's the basic algebra, or algebraic properties of these operations. So going back here, this is a way of writing vectors, this IJK notation. To see that any vector can be written like this, using this, you know, these basic algebraic properties, we start with A, which is A1, A2, A3. I can split this up using these properties. So this is really can be thought of as A1, 0, 0 plus 0, A2, 0 plus 0, 0, A3. Okay. I can pull this A1 out, treating it as a scalar. So this is the same thing as A1, the scalar, times the vector 1, 0, 0, plus A2 times the vector 0, 1, 0, plus A3 times the vector 0, 0, 1. But as I said, I is 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. And so really this is just A1 times I plus A2 times j plus A3 times k. Okay, so this always works. Any vector can be written like this. Quick example is if I have the vector A and that vector is, say, minus 1, 0, 3, I could also write A as minus I plus 0j plus 3k. Right? Now you might say again, you know, going back to what I originally asked, why would you want to do this rather than just writing it in, you know, what is a simpler form in a way up here? There's operations we're going to do on vectors that this can seem a little nicer sometimes, and it can seem a little easier to remember what it is you're doing. Okay. All right, and so this is just another way of writing a vector, but you have to know this because I am going to give you plenty of vectors in problems that are written in this form, okay? So you got to be able to write in either form. Okay. Now, going back to what I had mentioned last time, we have a notion of vector sum. Of course, we have vector subtraction, which is really also just vector sum. We have scalar multiplication, which allows us to multiply a scalar or a vector by a scalar. But we want to be able to multiply. All right, we want to come up with a product, all right, a vector by another vector. Okay. As I mentioned last time, though, if you just do what, is the obvious thing here, the resulting quantity just it doesn't get you anything. It has like no geometric meaning, and it's basically useless. So we are going to have two different products on vectors. So we are going to define two different products on vectors. Okay. And these are the dot product or scalar product or inner product. But we're going to use dot product usually, but these names are also fine. So that's the first one that we're going to talk about. And the second one that we're going to talk about is the cross product. Okay. Now both of these have some shortcomings. Okay. So first of all, the dot product is going to be really easy to compute. It will take you like 5 seconds to compute a dot product of two vectors. Okay. The problem with the dot product is that it's not closed. What we mean by that is if I take two numbers, right? So square root of 2 is a number, and negative 17, right? That's another number. If I multiply those together, then I get negative 17 times square root of 2, which is some other real number. Okay, so that is the notion of multiplication being closed. What that means is that I take two real numbers, I multiply them together, I get a real number, right? And that always works like that. I don't take two real numbers, multiply them together, and get something that's not a real number. And so the dot product, unfortunately, is not closed in that way. I take two vectors and I multiply them together via the dot product, and what I get is a scalar. It's not a vector, it's a scalar, and that's why it's called the scalar product sometimes as well. And, you might say, well, what's wrong with that? I mean, nothing is inherently wrong with that. The dot product is like one of the most useful things. As we'll see, the dot product is actually the thing that allows you to compute length. Which means it's very important because technically without the dot product in our Euclidean space, we had no way of computing length. So dot product is very, very important, but it is, maybe algebraically not ideal in the sense that it's not a true product because we take two vectors, we multiply them together, and we move outside the world of vectors. Okay, but so the cross product, however, is closed, but the problem with the cross product is that it is more complicated to compute. It will take you some work to compute the cross product of two vectors. And it has some unfortunate properties, like it's not commutative. So it matters in what order you cross the vectors. Like A cross B is not the same as B cross A, as we'll see. Okay. And so that is that's the idea. Okay. And so let's talk about the dot product. Okay, so actually, no reason to use a different sheet for now. What is the dot product? So I have two vectors, and I promise this is the last time I'm writing this out to save myself some time. So when I have vectors, this is the notation that I'm assuming I'm using. So I have two vectors, A and B. If I dot them, A dot B. So I read this. What is this? This is, I multiply each of the components, but rather than forming a vector with those products as its components, I sum them. So I sum the results. So this is A1, B1 plus A2, B2 plus A3, B3. So that's how I do it. Note, the result of dotting two vectors is a scalar. Okay. What is an issue that this causes? Well, there's no such thing as like a triple dot product, meaning you can't have A dot B dot C. That's impossible. And the reason why you can't have that is A dotted with B, for instance, would be a scalar, and then you'd be dotting a vector with a scalar, which doesn't make any sense. Dot product only makes sense if you have two vectors of the same size, right? So that means you have two vectors living in the same space, right? So you're not going to dot a vector in R2 with a vector in R3. I'm not going to get into that anymore, of course, because that's something you'll talk about in linear algebra. But the idea is that you start with two vectors, you dot them together, you get a scalar. So you have to be careful to keep track of what it is what kind of quantity you're dealing with. Let's do an example real quick. So let's say let A be, let's use our new notation since we're just trying it out now. So let A be 2i minus 4j plus 3k, and let B be 0i plus 7j, we'll say plus 5k. Okay, and so what is A dotted with B? Well, this would be 2 times 0 plus minus 4 times 7 plus, in here, this is the asymmetry here is bothering me, so let's just use parentheses for all these, plus 3 times 5. Okay, so this is 0 minus 28 plus 15. So this is minus 13. So I have two vectors there. I dot them together, and I get minus 13. Okay, but what does that mean? All right, if I multiply two numbers together, right, 2 times 3. Well, you remember how multiplication was originally formed for you. You can make a rectangle, right, that has width 2, length 3. Or if you're thinking of it as a counting problem, this is, the number of total objects in 2 groups of 3 or 3 groups of 2, right? So what does A dot B mean? If you dot two vectors A and B and you get minus 13, what does that mean? Well, it's not totally obvious immediately what this says. Okay, but there it is. Okay, now we can go through some basic properties of the dot product algebraically. This one example is basically all you need to compute to see how the dot product is computed, because as I said, computing dot product is really straightforward and easy, and once you do a couple of these, you're going to be able to do a dot product in like 5 seconds for most pairs of vectors. So let's see some properties. What if I have a scalar times a vector and I dot it with another vector? What's the relationship between that and, say, dotting the vector A with that same scalar times the other vector? Well, these are actually the same thing. Right? In fact, these are both also equal to just multiplying the scalar by the dot product itself. Okay, so this is our first fact here about the dot product. We could check this really easily if we wanted to. So I mean, what would I get here? So CA, right, is so CA1I plus CA2J plus CA3K. B as the usual notation. When I dot CA with B, what do I get? I would get CA1B1 plus CA2B2 plus CA3B3. And of course, I could factor out C. If I do that, I get this rightmost thing. I could move C over to multiply B1. I can do that because this is commutative, right? The multiplication of normal real numbers is commutative, so I can swap C over here. So swapping C over, multiplying the B, and then rewriting this is the same thing as A dotted with CB, for instance. Of course, there's a more straightforward thing to notice, that the dot product is commutative. It doesn't matter in what order I dot two things. Okay. All right. So these are my list of facts. Maybe I should say that whenever I start listing things here are our facts about the dot product. Okay, next. What if I say dot a vector with the 0 vector? Well, just immediately you see, well, 0 vector has 0 in each component. So then each component of A is multiplied by 0 and then summed. You're summing a bunch of zeros, so you get 0. Okay, so dotting something with 0 yields 0. Okay. All right, so that's nice. What about the relationship between scalar multiplication and, or maybe I should say, dotting a vector by another vector. So let's say that I use C for scalar here, so I don't want to use it as vector. Let's say that we have 3 vectors, u, v, and w. Okay, so we'll say u, v, and w are vectors. In general, a thing is a vector if it's got this arrow over it, right? So let's say that we have a vector sum of vectors, and we dot that with a third vector, w. This is u dotted with w plus v dotted with w. And I can also do it in the other direction. So I can, by commutativity here, right, this is the same thing. This is w dotted with u plus w dotted with v. So a bunch of nice properties here. Okay. Now, these properties, as nice as they are, ultimately this is not why the dot product is so nice. So why is the dot product so nice? Okay. Well, here's the reason. So first of all, before I get into the geometric meaning here, I could say, well, note that if I consider the length of a vector, right? So length of the vector A, that is the square root of a1 squared plus a2 squared plus a3 squared, right? Okay. What is A dotted with itself? So if I take a vector A and dot it with itself, what do I get? So this is a1 times a1, so a1 squared, plus a2 times a2, so that's a2 squared, plus a3 times a3, so that's a3 squared. So what's under the radical here is actually A dotted with itself. I'm going to rewrite that on the next page because this is important. So the length of a vector is actually the square root of that vector dotted with itself. Or, equivalently, a vector dotted with itself is its length squared. Now, this might just seem like a funny way of seeing a relationship between these two things, but actually, it's not. This is what gives length. The dot product is the thing that gives length. Okay, so the dot product is the thing that allows us to find the length of a vector. And so going way ahead for a second, so basically on Euclidean space, on say R3, I can define this dot product, and the normal length that we're used to comes from it. Okay, the reason why it's nice of thinking about it like this is that, say that I wanted to include the notion of time, right, as a fourth dimension added to my space. Well, then I could come up with a kind of sort of dot product on this space, on this four-dimensional space now. And that thing would kind of sort of play the role of this normal dot product. It would be very important. It would give us what's called a metric. Okay, and this is exactly the approach that, I mean, this is the building block. This is the very basic stuff that allows you to do, say, relativity computations, right? This is the starting point. Okay, so anyway, so then this is very nice. Obviously, geometrically, the dot product is completely entangled with the notion of length. Okay. So dot product gives us length. That's a very important thing already, that we wouldn't need anything else, right? That would be enough. But the dot product does some more things. So consider the following theorem. Okay. So let A and B be non-zero vectors. That means they're not the zero vector. Let A and B be non-zero vectors. And let theta be the angle between them. Well, we haven't talked about the angle between vectors yet, but remember, every vector can be considered as sitting with its initial point at the origin. So talking about the angle between them, even in space, right? In the plane, it's more obvious because there's just the plane. In space, you might worry, right? Like you might say, wait, do they lie in the same plane? Well, two non-zero vectors, if they're not scalar multiples of each other, determine a plane. If they are scalar multiples of each other, they determine a line, in which case the angle between them would be 0. Okay. So let theta be the angle between them. Then A dotted with B is equal to the length of A times the length of B times cosine of the angle theta between them. Okay. Now, what is the proof of this? I'm not going to do the full proof, but the proof is just directly from the law of cosines. Okay. So if you remember the law of cosines is a fact that you could apply to any triangle. One simple application of the law of cosines proves this. So if you want to, you can look at the textbook for that, but that's what's going on here. Okay. Now, using this, note I can solve for cosine of theta. Right? Solving for cosine of theta, I just divide by these lengths. I can divide by those lengths because these are non-zero vectors. Since they're non-zero vectors, they are not 0, which means their lengths are not 0. So dividing by these numbers is fine, right? Because I'm definitely not dividing by 0. So dividing by the length of A times the length of B, this tells me that cosine of theta is equal to A dotted with B over the length of A times the length of B. Okay. Y is being able to write, if I give you two vectors, A and B, dotting them is easy. Finding their length is also easy. And so given two vectors, you could write out the cosine of the angle between those vectors. Why is that a big deal? It allows you to compute the angle between two given vectors. So this allows you to find the angle between two given vectors using the dot product. Okay. So not only is the dot product tied up in length of a vector, it also allows you to compute the angle between two vectors. Okay, so let's see an example of this. So let's have the vector A, B. Well, let's actually do a 2D example. So let's have the vector A be 3, 3, and the vector B be, say, 5, 0. Now, you could spoil the fun if you actually just drew this, and I'll do that in a second. So if you think for a second, you actually already know the angle between these two vectors really quickly, but let's watch and see how this works. So I need to compute three things, right? So I need to compute A dot B. That's not too bad. So A dot B is 3 times 5 plus 3 times 0. So that's 15. Okay, so A dot B is 15. What is the length of A? So the length of A is square root of 3 squared plus 3 squared. So this is square root of 9 plus 9, so square root of 18. Okay. All right. And length of B is what? So length of B is, I know what it is, it's 5, but I'm going to write it out like this anyway. So this is 5 squared plus 0 squared under the radical. So this is square root of 5 squared, or 5. Okay. All right. So then cosine of theta, where theta is the angle between A and B, is A dot B over the length of A times the length of B. So this is 15 divided by square root of 18 over, or times 5. Okay. So I can do some simplification here. 15 is 3 times 5, so I have 5 in the denominator, so I have 3 over square root of 18 is square root of 2 times 9, so that's 3 square root of 2. So this is 1 over square root of 2, or I rationalized the denominator, which of course you were probably beaten in high school with always your teacher's probably always telling you to rationalize the denominator. Doesn't matter typically, but it can help you to recall what's going on here. Cosine of theta is square root of 2 over 2. So what is theta? All right. So theta in this case. Remember, when you have trig equations, right, you might normally have to think quicker about like what quadrant you're in, but here you're talking about two vectors and the angle between them. So clearly you're picking the smallest, right, positive one. This is pi over 4. Yeah, exactly. Okay, pi over 4. Okay. 45 degrees. Degrees is for cooking, right? We're radians only here, right? So anyway, that was it's an ancient joke my high school math teacher always used to say. Except he said it in a funnier way because he always grumbled. So it was more like degrees are for cooking, that kind of thing. Anyway, so pi over 4, right? And of course, if you drew this, then you would automatically know what it is going on here. So 3, 3 is here, right? There's 3, 3, and of course 5, 0 is like here, right? So of course, if you drew this picture, you would see automatically that this angle theta is pi over 4. Okay. All right. So that's nice. Okay. What else? Note. What if theta is pi over 2? Well, if theta is pi over 2, then A dot B is length of A times length of B times cosine of pi over 2. Well, what's cosine of pi over 2? Well, that's 0, right? Cosine of 90 degrees, right, or pi over 2, is 0. And so A dot B is 0, even when the length of A and length of B are definitely not 0, right, because A and B are non-zero vectors here. Right, so this is 0. So if the angle between the vectors is pi over 2, their dot product is 0, and the converse is also true. So the converse is also true. What does converse mean? Converse of an if P then Q statement is if Q then P. So the converse would be if the dot product is 0, then the angle between them is pi over 2. You can get that in the exact same way by looking at this formula. If A and B are non-zero and this quantity is equal to 0, then what's the only possibility? The only possibility is that cosine of theta is 0, and that happens when theta is pi over 2. So, big fact, which is very, very important. So, if you dot two vectors, right? So these vectors dot together, this is 0 if and only if A and B are perpendicular or orthogonal, which means perpendicular, which means the angle between them is pi over 2. Now you might say, wait, can you really make this statement? Because you didn't say anything about A or B being the 0 vector. What gives, right? What if A is the 0 vector, B is any vector? I dot it with any vector and I get 0. Well, that's fine. The way that we make sense of that is we just say that the 0 vector is perpendicular to every vector. Okay, so 0 vector is orthogonal to every vector. Now, of course, that doesn't help you that much. You can't see an angle between the 0 vector and a non-zero vector. So this is purely just for making this statement simpler so that I don't have to add a ton of caveats here. But that doesn't affect anything, right? You know what's going on here for the most part. So yeah, so someone else said 3 pi over 2, but that's exactly the point, right? It's think about what you're finding the angle between two vectors. So you're picking the smaller one, right? The one that makes sense. The second you have an angle, right, between the two vectors, you're picking the smallest positive one as being your angle between them. Of course, you could come up with a convention where you use another, but of course all of these, the angle between two vectors is always going to be between 0 and pi, right? So that just keeps these trig equations a lot simpler, because you can always find one of those vectors, or you can always find the angle between 0 and pi. between the two vectors. One more thing before I end. I know I'm a little bit over, but one more thing before I end that is not quite related to this, but it was related to what we did when we drew the, or when we first wrote down or solved for cosine of theta. And it's that, so an unrelated fact, well, it's not entirely unrelated. And this is from, I meant to mention this at the beginning of class. Let A be a non-zero vector. The second you have a non-zero vector, what does that mean? Well, among other things, it means that the length of A is not zero. Right? Thus, if I say take the vector A and I multiply by the scalar 1 over the length of A, i.e. I divide the vector A by the number, right? The length of a vector is just a scalar. So I have a vector here that is A over the length of A. Okay. This vector is something special. Before I can say that, I have to make a definition. So a unit vector is a vector, we'll call it U, such that the length of U is 1. That's the unit vector, or that's what a unit vector is. It's just a vector whose length is 1. This vector A divided by the length of A is the unit vector in the direction of A. Okay. This is a very standard trick. Okay. Given any non-zero vector, you can always find a unit vector that points in the same direction. Why does it point in the same direction? Note that all we did to A is scale it by some scalar. Right? So by definition, this is parallel to A. But what we mean when we say parallel, of course, is that the vectors point in the same direction. So this is the unit vector that points in the direction of A. Now, if A is already a unit vector, then you're dividing by 1 here, and so A is already the unit vector in its own direction. Right? Okay. This is a useful trick, and it's going to come up in a lot of the computations we're about to do. Anyway, so I'll talk about the dot product again for like 5 minutes on Monday, and then we will do the cross product. So we should finish cross product by the end of class Monday, which means that we'll start 11.5 next Wednesday. So your first homework I'll assign next week. It won't be too long, and you'll have a few days to do it. But I'll post that, like I said, next week. So anyway, until then, I will see you. Have a good weekend. I'll see you on Monday.